of course, the measures on xy is a subset of the measure on x. Yeah, this is. I could have said that this is a section of a certain vibration. Kind of try to use less words. So I don't want to give a full proof now, but I want to describe it. It is important term, not too easy for beginners maybe, but certainly for those who knows Ries integration, Radon-Nikodym derivative. It is not hard to prove. Let me explain this. Basically, what am I doing? I think I did describe. Well, we did describe in full how to push measures. This is very easy to do, and I can actually push L1 functions. I think about those as measures, and I push them. Actually, maybe I should stop. If I have an L1 function, stop and say the following. If I have an L1 function here, I can think about it as a measure and push it down and get a measure here, which is well, what do you mean? I have mu here, and if you have an L1 function f, I can have the measure f times mu here. A measure which is absolutely continuous with respect to mu. I can push that measure here, and I will have some measure which is easy to see to be easily seen to be absolutely continuous with respect to nu. So by Radon-Nikodym derivative, it is some f bar times nu. So f bar is the push of f. Let's think about it this way. Okay? From where I am standing, knowing the theorem, actually I know what f bar means. F bar is the integration over fibers, as I described here. But we don't know this one yet. This will come up as a bonus. But we do have, we can define, even without introducing the fiber-wise measures, we can define that push, f bar. Again, by the Radon-Nikodym derivative. And f bar will be an L1 function. Even if you have started with a continuous function f, the result f bar will be only L1 function, so it will not be defined everywhere. So, but it will be defined almost everywhere. So now, don't do it for all L1 functions on x. Take just a dense collection in the continuous function on x as your test functions, and do it to them. Push them down. Each of them will define a full set in y. Take the intersection of these. This will be the almost everywhere that appears here. Take countably many test functions in x, push them down, and think of these L1 functions. And now, I want to claim that each point y define for me a functional on these countably many functions. Just evaluation at the point. Right? If I have a function, I push it down, and on the domain that are all defined, I can evaluate the function. For a given y, I'm getting an evaluation at the point. So this is a functional on this dense subspace of functions here. It is a well-defined functional. But this functional is easy to see. Now I have to write down things, so I'm not doing it precisely, but it is easy to see that it is of norm 1. So it extends to the full space. So it doesn't really matter what kind of dense subset I was using it to begin with. It extends. So it gives me a function on the full space of functions Cx. And this functional on Cx associated with the evaluation at y will be the guy mu y that I'm seeking. Okay, so for those of you who are happy with oral explanation, I hope you are happy. If you find yourself that this is hard to follow, just look it up in the literature. But this is an important piece.
How much is compactness and the price of the is important here?
Also, again, I want to end this class, so I don't want to formulate again another theorem. But it is not important at all. I can replace x and y by the spaces, just picking the models. And maybe I should say, my last remark is, typically, when I will use it maybe in the future, X will be a tame action of G, and Y will be the space of orbits. And the result here will be that if you have a tame action, every measure on it is actually disintegrate nicely to measure on the space of orbits. Okay? So I need tameness in order to make this a nice space, so I can apply this theorem. But this is, yeah. Basically, this process of disintegrating things into G orbits is called ergodic decomposition. But in the presence of a tame action, this is something very, very nice and explicit. So this is the end of my talk.